Hello and thank you for watching. In this video we're going to define the scalar product and talk about its properties. So jumping right in, the scalar product it's a function that maps a vector, or is a function which takes two vectors in Rn and maps them on to a real number. So what I'm saying is that if we dot a vector with another vector in the same real space, then we just get a real number. Okay. So to define it properly, if we have some v dotting with some w, writing it as its components, we have that this is equal to v1 times w1 plus v2 w2 plus vn wn. So what we did here was basically we just took each element of the vector and then multiplied it by its respective component and then added it to the rest. So we took v1, multiplied it by w2, and then added it to v2 multiplied by w2, v3, w3, added them all together. And we can also write this as the sum from I equals 0 to n of vi, wi, oh, not 0, 1 from 1. Okay, so now we're going to talk about the properties. So firstly, it is symmetric, which is the same thing as commutative, but we wanted to say symmetric in this case specifically for vectors, which means that u dot w, or v dot w, is equal to w dot v. It is linear in the first factor, which means that, well, it means two things. So firstly, we have that for some vectors u, v, and w, this is equal to u dot w plus v dot w. So we basically just distributed it out on the left hand side. And we also have that if we have some real number lambda multiplied by u dot some v, we have that this is equal to this is equal to some lambda of u dot v. Okay, so it's linear in the second factor, which is almost the same thing. However, we're just looking at the second terms instead. So we have u dot v plus w is equal to u dot v plus u dot w. Okay, nice. And then we also have, if we have some real number lambda, or if we have a vector dotted with some real number lambda multiplied by our v. This is still equal to lambda u dot v. And together these two properties mean that it is bilinear. Okay, and the last property is that we have positivity in the sense that if we dot a vector with itself, it's always going to be greater than 0, which intuitively makes sense because let's say we have some vector and dotted with itself. This is going to be v1 squared plus vn squared, which means that all the terms are square numbers, which means that they're greater or equal to 0, which also gives us the equality case when we have v as a 0 vector. Okay. So, following on from this, this second term, this term looks oddly like our definition of magnitude in, well, if we have the Pythagorean theorem, we have a squared plus b squared equals c squared. This is the hypotenuse of a triangle. We can generalize it in more dimensions, equals d squared and so on. So actually, if we have n dimensions, we actually have that the distance from the origin, we define the 0 vector as the origin of our Rn space. If we have this is equal to the magnitude of our vector, and so we have that v naught v is equal to the magnitude of our vector. Okay, so now I'd like to consider a specific case. Let's consider n equals 2. So let's say we have some graph and we want to take a point on this graph. And then we can define this point using our x component and our y component. However, what we could also do to uniquely define this point is, well, if you look at its distance from the origin and its angle, we can also define the point using this. So, say we have some triangle or on the graph. So let's say this is an angle theta, this is a distance r away, this is our y, this is our x. So our simple observation tells us that x equals r cos theta and y equals r sine theta. So this tells us that we can also write a vector, a vector as r cos theta sine theta for n equals 2. Okay, so that's nice. However, what if we have an r of 0? What if we're at the origin? Then we can't find an angle, because surely it could be going this way, it could be going that way, it could be going this way. So we only define this to be the case for r being greater than 0. Okay, now we're going to derive a useful expression for the case n equals 2. So suppose we have a vector equal to r cos alpha sine alpha, and vector w equal to some s cos beta and sine beta. Now, if we dot those two, we get that we have r rs multiplied by, well, I shouldn't use a dot in this case, multiplied by cos alpha cos beta plus sine alpha sine beta. However, we may notice that this is just cosine in the first place, in the sense that we have cosine alpha minus beta, which, okay, what is alpha minus beta? So we have some angle alpha. Oh, we have some angle alpha, and we also have some angle beta. So this angle in between our two lines is alpha minus beta. So we can define the dot product of v dot w equal to, well, rs cos theta, where theta is the angle between v and w. And we know that our r and s, they're just the magnitude of our vectors. So we have v dot w is equal to v w cos theta. Now this is the case in 2 dimensions. However, it actually follows that it's the case in n dimensions. So even though we proved the case for n equals 2, it actually holds in Rn. And that's about everything I wanted to cover in this video. I will make a video with examples shortly. Thank you for watching. Bye bye.